coming today. This morning for you, it's about 9 o'clock at night for me, where I am in Atlanta, Georgia. And today's seminar is on Oracle insert statements. And as in the last presentation I did, there are a lot of slides that are up front at the beginning of the presentation, which I will spend no time going over. Those are things that if you want to review them later, you certainly can look at them, and they're there to keep my company happy, but there's no reason for me to spend any of your time talking about them. The one thing I do always want to do, of course, is Oracle has their safe harbor statement in which they essentially say you can't rely on anything that we tell you. It's sort of an indication of where we might be going in the future, and I'm going to talk about nothing that isn't already in released product that's been out for at least a year or more, in some cases more than 25 years. So I think you can safely rely on what I'm going to tell you today. So the introductory slide, which is who I am, my website, the kinds of things that I get involved in are all things that you can pretty much skip over. And Francisco, you can just gently tap your way through to slide 10. Or 11, or even, take us up to slide 12. Just tap, tap, tap. Let me know when you get to 12.
Go ahead.
Okay. I thought I'd put this slide in here just because I got back from Lima, Peru about 36 hours ago. I was down on the Latin America tour, and I thought that I would honor Francisco because the very first time I was in Peru, I was there with him, and with an invitation from him to go and do that. And I just wanted to use this opportunity to say thank you to Francisco in a very public forum. I am still going to Pescados Capital, and I'm still drinking all of the pisco sours I can possibly survive. So let's go ahead and just continue very slowly and move on to slide number 15, content density warning. There is a lot of material in this presentation, certainly more than one would normally try to put into a one-hour presentation. And again, it's here primarily because I wanted to make sure everyone had a resource to review later. And if you have questions about any of this material, feel free to send questions to Francisco, or my email address is included in here. Go right ahead and send them to me, or if you have Skype, feel free to just call me on the phone. Preferably not at 3 o'clock in the morning my time. So let's move on to slide 16. And I want to talk for a second about why I, as someone who was an ACE director for almost 10 years, and someone who's been involved in IT and Oracle now for almost 40 years, well, I'm wrong, almost 50 years, would spend time talking about insert statements. And part of the reason I like to talk about insert statements, and a lot of things that people would call basic and go, well, I know this material, I don't need to study this. I was in Oracle for 2 hours and I knew how to do insert statements. A couple of years back, I was with Tom Kiten, and we were in fact in Lima, Peru, and we were in fact at Pescados Capital. And we were talking about how much we didn't know. And one of the comments that Tom made at that dinner was, I don't even know all the syntax for insert statement. I have to go look it up. And I thought, well, if Tom doesn't know it, I sure as heck don't know it. And that pretty much means that probably nobody else knows all of that syntax either. So Oracle University doesn't teach it. There are no books that contain this information. And I just wanted to pull together all of this stuff to give people an indication of how rich an environment the Oracle database is, how much you can do in it, and to show how important and critically important it is to study the Oracle docs and not just assume, well, I know something, therefore I can skate by. So let's go to slide 18. And insert statements are part of what we call DML, data manipulation language. It's the parts of the SQL language that we use to manipulate rows of data. So it would be insert statements, updates, deletes, and merge statements. I'm going to mention merge statements very briefly here today, but for the most part, This will be entirely focused on insert statements and some of the things that are related to insert statements, such as the design of the tables in which we insert rows. So the syntaxes for insert statements, if you were to just try to give them all names, the topics I'm going to be talking about today is what I call basic insert. And basic insert is what I think every single person in this audience knows. So we'll spend less than 60 seconds on it. And everything else in here is the material that when I presented this at many, many user groups over the last couple of years, I have found that almost nobody knows. And in some cases, nobody knows it. And then there's also a whole group of insert statements that are related to the use of the PL/SQL language. There are aspects of insert statements that directly impact performance, and in some cases very dramatically. So let's go ahead and move into part 1 and slide 23. And I want to start off with this insert statement, and I promise less than 60 seconds on it, because this statement and the next slide are essentially the only ones that I can pretty much guarantee everybody knows. You say insert into, you name the table, you give it one or more column names, the word values, preferably you use the word values. If you don't use it, there are errors that can be generated by not doing that. Although it's optional in some respects, there are lots of ways to make mistakes if you don't say values. And then a list of values. So on slide 23, it's showing a single value. On slide 24, showing that comma delimited form with multiple values. At that point, which is about 1 hour into learning the SQL language, maybe 2 hours into learning it, everybody says, okay, I've now mastered insert statements. I'm a developer. So let's move to the next slide, number 25. This insert statement has been in Oracle now for so long, I can't even figure out when it first came into Oracle. I can't find documentation that old. I probably have some Oracle 5 and 6 books at home I could dig out of a box. Maybe I wouldn't find it at some point. But this has been in Oracle for every version that anybody in the country of Australia has, that's for sure. Maybe even people in New Zealand. And what this is a conditional insert. It's an insert statement that in essence contains a case statement built within it. So if you look at the bottom left-hand quadrant, insert when. The when is like case when. It's a conditional. And it says if the department number in the row that I'm inserting is 10, then put it into the emp_10 table. If on the other hand it's 20, put it into a different table. If the department number is 30, put it into another table. If it's any value that isn't a 10 or 20 or 30, just like an else statement in a case or an if statement, put it into a completely different table. So I can essentially go to a single source table and with one IO against that source table, do the equivalent of 4 insert statements worth of work, or 10 insert statements. There's no seeming limit on the number of these that one can do. And I can now take the information from one table and partition it into multiple physical tables. If you look at the version of it on the right where it says insert all instead of insert, these are really just 2 different syntaxes for the same thing. The word all is optional. Let's go to the next slide, number 26. This is another version of a conditional insert, but this one does something a little more interesting. I insert simultaneously every record into multiple tables. So my select statement says select the program ID, delivered date, customer ID, and order date from a table called airplanes. This is in fact a production table at the Boeing company, so it's a small piece of a production table at the Boeing company, but illustrates the point. You go into this massive table of airplanes, and you say, pull out all the airplanes. And some of the information I want to put into the customer table, and some of it I want to put into the orders table. So the program ID goes into both tables, but the customer ID only goes into one table. The delivered date only goes into one table. The order date only goes into one table, all from a single select. So it's much faster. Rather than going through this massive table twice, I only go through this massive table one time. Let's go to the next slide. Here's another version of the insert with a condition. And here you'll notice is rather than saying insert or insert when or insert all when, this is insert first when. It stops at the very first condition that has a match. With the insert all, it will insert into every target table that matches the condition. So you could have multiple overlapping conditions. You could have conditions that said greater than this or between that or in multiple values. You can do any Boolean logic you want in any of these. In this particular case, it's saying when I find the very first match, do that insert, and then immediately go to the next row. So it's only doing a single insert, whereas the previous ones could all do multiple inserts. Let's go to the next slide. This is another one that I think we can pretty universally say that most people know, in a sense, but have probably not done. And this is inserting into a select statement. You write a select statement, and just in the same way that you might do a create view by writing a select statement, here you don't materialize the view as a physical object stored in the data dictionary. You just take your select statement, put parentheses around it, and now you can use that as the target for an insert statement. In and of itself, this is the most useless, worthless piece of syntax I can imagine, because it really doesn't do anything you couldn't just do in your normal insert statement. But let's go to the next slide, and let me show you how I very simply modify this to give it value. On slide 29, you'll notice I've created a table. The department number is not null, the department name is not null, but I allow any location based on the table definition. But from an application standpoint, I'm inserting into a select statement, but I've now added a where clause to the select statement. It says where the department number is less than 30 with check constraint. I've essentially now put a check constraint on the underlying table in terms of what data it has. Now you think to yourself, well, I want to put a check constraint on the table, I'll go put one on. But you wouldn't do it if you had an application like eBusiness Suite or Siebel or SAP or PeopleSoft or something else where the person you bought the application from included rules that said you can't modify our application. Well, you're right. I can't put a check constraint on your table, but there is nothing that prevents me from putting a check constraint around my insert statement by inserting into a select. So this is another version of the insert statement, and it's not something that you're going to use every day. It's probably not something you're going to use every month, but from time to time, this may be the right solution to solve a tricky problem where you can't go in and change application code. Let's go to slide 30 and talk about inserting into a view. I just mentioned that when I write a select statement, put parentheses around it, it's essentially the same as creating an in-memory view rather than storing a view on disk as a physical object or as a logical object. When I said that, it was sort of implicit in what I said that you can insert into views. But it's not always true that you can insert into views. You can insert into simple views where there's a direct one-to-one mapping, but you cannot insert into views that have group bys or other or aggregating clauses such as max, min, average. So it's critically important to be able to know which views can I use as targets for insert or any DML operation, and which ones can't I? So I want to call your attention to a database data dictionary view called Updatable Columns. Now, if you're in an older version of Oracle or you're not working with a container database, you might want to look at DBA Updatable Columns. I tend to like to get out there on the cutting edge and do PDBs and all of the hotter things that give me better performance and better quality work. So I'm using the CDB version of this here, and you'll notice that I am essentially using CDB Updatable Columns to figure out which columns can I insert in, or there's also the ability to look in there and see what can I update, what can I delete, and then join that with CDB Views which allows me to say which views can I use for inserts, which ones can I use for updates or deletes if I wanted to look at those columns. On slide 31, I talk about another form of view, and this is a view form that, from my perspective, every developer since 11.2 should have been creating like mad. There's really, once we had additioning views, no excuse for ever touching a table. You should never put a trigger on a table. You should never insert, update, or delete on a table. You really should be working through additioning views, because additioning views give the ability to do things far more flexibly than going directly against tables, and they will never, ever negatively impact performance. So you're getting flexibility at zero cost, and that's a hard thing to argue against. But all additioning views are updatable, meaning you can always use them to insert, update, and delete. You never have to say, it's an additioning view, can I? If it's an additioning view, you can 100% of the time always use it for DML, and use it for any DML you want. So this is my way of encouraging everyone, pay attention to addition-based redefinition. If at the end of my presentation today, you feel like maybe you need to go back and start reviewing the docs, let this be a flag that says, oh, and I better look up addition-based redefinition, because it is literally the hottest new technology that came out in Oracle 11. Unfortunately, for people using it, it was free. And when Oracle gives something away for free, the salespeople don't know about it, people don't go to conferences and talk about it, nobody writes books about what's free, so hardly anybody ever heard about them. But they are literally the hottest thing that hit 11.2. Let's go to slide 32. And slide 32 is in here because it points out another one of these little interesting things about insert statements that hardly anyone realizes. Oracle says, and it used to be true, that you can treat a partition table just like a regular table. You want to select from it, you don't have to tell Oracle which partition the data is in. You say select, Oracle figures it out for you, which partition has the data you want. You want to insert, Oracle will insert into the right partition, or update the right partition, or delete the right partition. It used to be true, it's no longer true, and there is one exception. So I want to call this out, and I want everyone to take a second and glance at this error message in red, because that error message contains the information that is crucial to knowing when you have one of these partition tables where you can no longer treat it like any other table. And the message says, partition by the system method. System partitioning is something that Oracle has done partitioning that follows in line with the way Oracle has always treated developers and DBAs, which is essentially with a lot of respect. They're not like Microsoft. Microsoft says, oh, you want an extent? Guess what? All extents are 64K. You want a block? Oh, blocks are always 8K. We can't afford to have you actually think or tune or use your brain and your expertise, so we're just going to decide everything for you. Oracle says, you want to build indexes? Fine. We will give you a framework, and you can create indexes that we never imagined. Oracle says, you want to do locks? We'll give you a built-in package called Dbms Lock. Go create your own locks that do things no Oracle lock ever dreamed of doing. Oracle's also done the same thing with partitioning. And system partition tables are tables in which you write your own function that evaluates the data and decides which partition it goes into. So Oracle's saying, we will let you create partition tables, but if you want to do 3-level partition or 12-level partitioning, or you want to partition by some crazy concatenation thing that uses a function, a PL SQL function you wrote, go knock yourself out, have fun. We're going to give you the ability to do it. When Oracle gives you the power to make that decision as to where the row goes or where to find the row, it means that the database doesn't really know where it went. You're the one that made the decision. So in this case, you do have to call it out. You have to tell the database where. So you have to use that same function you use to make the decision to also say, when I insert, I have to tell it where to insert. When I select, I have to tell it where to select from. But I still get the value of partitioning, and that's really, really valuable. Let's go to slide 33. Slide 33 is one I want to use to introduce a very, very old topic. And it's so old that almost no one alive today in the Oracle world even remembers it exists. And that topic is something called a cluster. Now, normally in an Oracle database, and for that matter in Sybase or Informix or DB2 or SQL Server, a 8K block or 8K page can only contain the contents of a single object. So if you create a table, the table has an initial extent. It consists of that initial extent. It's got some blocks that only contains data from that table. But that's not necessarily a really efficient thing to be thinking about. So when Oracle was first designing the data dictionary, they came up with the concept of a cluster, and the entire Oracle data dictionary, from the standpoint of those pieces that are most important from a performance standpoint, all don't store information in table spaces. They store it in clusters. And what a cluster allows them to do is to put information from multiple objects into the same 8K block. So think about the situation where you're going into the data dictionary and you're saying, I want to select from this table. So what does Oracle need to know? Oracle needs to know, does the table exist? Okay, great. What columns are on that table? Yeah, that would be important to know. Let's see, what else would I need to know? Oh, what indexes are on that table? What constraints are on that table? All stuff that Oracle has got to know to work with that table. Why go and select from an index, select from a table, then select from another index, select from another table, select from another index, select from another table, just to get stuff that every time you ever want it, you're always going to be selecting from those same 4 tables or 12 tables. Oracle's original concept behind the data dictionary included this object called a cluster, where they could co-locate the row about the table with the rows about the column, with the rows about the constraints, with the rows about the indexes, with the rows about all the other stuff that were critical. So in this little code example here where I query DBA clusters, what you notice is that there are a number of cluster names. Take a look in particular at C_TS number sign, table spaces, OBJ number sign, objects, file block, mlog, materialized view logs. You can start to understand the way Oracle thought about doing this. So back in the very, very old days, 30 years ago of Oracle, we had single table hash clusters that contained a single table and a hash index for very fast access. There were also multi-table hash clusters and index clusters, and very recently as in about 12, 15 years ago, Oracle added something called a sorted hash cluster. And on the next slide, 34, I've got a little more information showing you, for example, in cluster OBJ number, the different types of objects that Oracle co-locates within a single 8K block to make sure that you're getting the best possible performance. Tab $ for tables, LOB $ for large objects, IND $ indexes, CLU $ clusters, COL $, columns, column types, index column dependence. It all just flows right out of there. This is why the data dictionary can achieve such incredible performance. But this is all fully supported and fully documented in the Oracle SQL reference, and there's nothing that prevents Oracle developers and DBAs to go, I've got situations where a 10-time speed up would be a heck of an improvement for our application. Let's go talk to the developers and explain to them about these objects that are older than they are, and maybe solve the problem by building objects the right way. So on slide 35, I show an example of the most recent version of this, and it's called a single table hash cluster, a sorted hash cluster. And what it combines in an 8K block is one table and a sorted hash table. So it's not sorting the data, but it's sorting the hashes of the data. So my first DDL statement at the top, create cluster, shows that I'm creating a cluster, and I'm saying I want the hashes sorted by the line ID and the delivery date. In my second DDL statement, I create SHC airplane. Again, this is in production at Boeing, or certainly was a few years back, in which we are saying, I'm not going to store my data in a table space. I'm storing it in a cluster called sorted HC, which I just built above. And I'm identifying the line ID and delivery date columns as corresponding to the sort information I gave when I created the cluster. Every time I insert a row, the rows go in just like they do in a normal heap table. They just get slammed in there. But the hashes get sorted, which is extremely fast. When I query that table later, I get the information out in that sorted order with no overhead. There's no order by clause that has to execute. There is no use of the temp table space. It just says, this is the way you want the data back? Fine. When you ask for it, we'll read the hash table, we'll give you back the data in exactly that order, and you pay no penalty for what could otherwise be a very expensive, very, very ugly order by clause. If you use a different ordering than the one that's here, then it's just like any other table. But if a lot of the time you're using a particular ordering and it's expensive, you can eliminate 100% of the overhead of that ordering. Okay, let's go to slide 36. Another part of being aware of insert statements and the implication of insert statements is that there are two column types that very few people in the Oracle universe are aware of. One is what we're called virtual columns. And virtual columns are columns that aren't stored as part of the table, but are there virtually, meaning Oracle virtualizes the answer during an insert or an update. So in the example I've got here, I've got the following business problem. The business problem is that I know that we need reports that say, give me all the people whose salary fits in a particular range. Well, not their salary, really their total income. And for the salespeople, total income is a combination of their salary plus their sales bonus or their commissions. So how would I know what a person's total compensation is unless I go through and take their salary and add it to their bonus and add it to their commission and sum it and say, now, does this fall within the constraints of my where clause? If it does, great, I got the answer. And if not, no, I throw the row away after spending all that time reading it and calculating it, and I go for the next row and do the same thing again. It forces me into a full table scan, and it forces me into doing massive amounts of calculations on the fly. With a virtual column, I can say, as you are inserting this data, materialize it for a quarter of a millisecond, and now index it. So while the data, the results of the calculation are not stored in the table, they are stored in the index. Or maybe I want to say nobody can make negative dollars. That sounds like a reasonable thing to do for a payroll program. How would we do nobody can make negative dollars if some people might have no salary and be paid entirely by bonus? Again, I've got to do the calculation. So I can also put on a check constraint. And the check constraint can use the virtual column to say that the sum of salary plus bonus plus commission, not less than, build a check constraint on that. So using constraints or indexes, virtual columns give me tremendous power, but I cannot insert a value into them. They look like a real column when I do a describe on the table, but there is no physical storage. So I have to say, I know the sum of 1 plus 2 equals 3, but I cannot insert the 3 because that column doesn't exist. I will insert 1 plus 2. Oracle will materialize the 3 and then use that. Let's go to the next slide. This is another type of column that Oracle has built, which can be very, very powerful when you're aware of it and use it in the right place. And it's called an invisible column. And invisible columns are real physical columns. So whereas the virtual column looks like it exists but really doesn't, this is one that really does exist but looks like it doesn't. A little bit like the two were made for each other. Oracle uses invisible columns for a lot of things. They use it for temporal validity, which, if you're not familiar with temporal validity, is something that's not part of what I'm going to be talking about today, but it's something you should definitely make a note to yourself and look up and understand. They also use it for all of the geospatial applications that Oracle has had in the database for a very long time. This is not a good place to hide passwords. The fact that the column is invisible doesn't mean that somebody can't query it. But what it does mean is that somebody looking at the data dictionary and doing a scribe on a table will not know that there are some columns that are there. And those columns could be holding things that are maybe checksums, for example. It's not like I need to hide the checksum, but then I don't necessarily need to have everybody in the world looking at a column called checksum. So I might create an invisible column that's a checksum that allows me to validate the column and the data that's in it, or the row and the data that's in it. Let's go to slide 38. This is another one of that very small group of insert statements that, from my experience, pretty much every developer and every DBA knows. And it is a create table as. So we create a table as the result of a select statement. It's very straightforward in the context that I'm showing it here. But what I find almost no one realizes is that you can create table as any select statement you are capable of writing. It doesn't have to begin with the word select. It could begin with the word with as a common table expression. It could be a combination of inner joins and outer joins. You can cast values. You can choose different columns from different tables. You can manufacture, using a select statement, any table you want, with or without data. If at the end of a create table as statement I write where 1 equals 2, it will create the table and load no data, because where 1 equals 2 returns a logical false, and it says, I'll build the table, but look, nothing matches my criteria, therefore I will load no information in it. So experiment with create table as, and you'll find these are extremely powerful for building tables and always getting the column names right, always getting the data types right, always getting the constraints right. There's a huge amount of power in looking at these as being a lot more robust and a lot more capable than what we normally see. Let's go to slide 39, and then I will follow that up by going to slide 40. And the thing I will tell you about this is I'm going to show this to you in the interest of being complete, and I'm going to say, please don't do this. Back in Oracle 8.0, Oracle was feeling pressure from what appeared to be competitors coming onto the scene who were touting the fact that they had object databases. So C++ was an object language and Java was an object language. And these people were going, look, the applications are objects, therefore our databases should have objects. Well, they were sort of right if one didn't care about A, wasting space, B, rotten performance, and C, and most importantly, a total lack of data integrity. Because objects are precisely that. They are objects. So trying to guarantee the uniqueness of an object is remarkably difficult unless you can somehow stamp a serial number on it. And if you have a column full of serial numbers, from an object standpoint, it looks like a document. You really can't do that, so therefore you're back to being relational again. So this is here, again, just to show you how to create an object table. And you'll notice that course list, I've created a type called course list, and then I use course list in the same way I would use date or number or timestamp or varchar to define a column in a table, and then I have to again refer back to course list in order to be able to insert into that nested table. On slide 40, I have another version of this that instead of using a defined type, uses a V-array, another object type that Oracle had. And again, it's a marvelous thing to behold, but do not use these. It's good to know that they exist. It's good to know what to do if you ever bump into one. You'll recognize it. You'll know how to handle it. But I would encourage everyone to not create any of these. Let's go to 41. This will be the one and only time I think I will mention merge statements. No, there's one other time I'll mention merge statements today. I personally don't like merge statements. And I've got a reason for not liking them that has nothing to do with the syntax. It has to do with mathematics. And the mathematics is this. If you look at this merge statement, I have a statement that runs a select statement. For every single row, it runs a select statement to see if the row matches the criteria. When matched, when it finds it, it updates it and then deletes, and then does a delete. If it doesn't find it, it then inserts a value. So, what are the chances when you're running an application that you, as an application developer or a DBA, are so clueless about your application and are so clueless about your data that you don't know whether the row will be there or not? Well, you may not know this row. You may not know that other row over there. But you know, or you should know, that 90% of the rows will be there and 10% won't. Or 96% of the rows will never be there, but 4% might somehow manage to be there. If you know for anything that's at that edge where it's 80 or 90% of the time it is either there or not there, rather than running that select statement 100% of the time and getting back a totally predictable result, it is more efficient to just say, I'm going to insert everything on the planet. If I have an exception, I'll say exception when others then do the update, do the delete. Or if I know the row will never be there, will always be there, I'm going to go run the update. If the update fails, skip the delete, do the insert. If the update succeeds, do the delete and move on with your life. So from a pure math standpoint, know your data, know what the chances are that you are going to have a success from a select statement. And then, if it makes you feel better, and probably should make you feel better, do a little testing and make sure that the math works out. But it should almost always be faster to do a small amount of exception handling than to run a select statement on every single row that you ever encounter. Let's go to the next section, which is part 2, PL/SQL insert statements. What I find fascinating is that the vast majority of insert statements that I see people putting into Oracle tables are not PL/SQL insert statements. In fact, they don't even realize that there is an entire class of insert statements designed around PL/SQL to optimize coding, to optimize maintenance, and to optimize performance. So let's go ahead and move to slide 43. And let me show you the worst possible way to do insert statements within a PL/SQL program. The worst possible way that you can do it is with a cursor loop. And a cursor loop is the death of performance because it inserts one row at a time. And Tom Kite used to use a phrase that was row by row, slow by slow. Every time I do something, I have to insert it. I have to check the primary key. I have to check the foreign key constraints. I have to check the check constraints. I have to make sure that this is null or not null. I have to go fire a trigger. On and on. I have to maintain the indexes. It just goes on and on. It's staggeringly slow. The statement that I'm doing here is I'm hitting a table called parent. I am multiplying the part number from the parent table by 10, and then I'm inserting into a table called child. Let me show you one brief precursor leading up to the way that should be done. The precursor is that you'll notice here that what I have done is I have declared a variable named trec, which looks like a row in a table named T. This is really interesting. If the table changes, if I add a column, my trec changes to match it. If I change the data type, it changes. Any change I make to that table, trec will change. When it comes to inserting values, I assign my values in memory. So my table has two columns, table name and table space name. I'm going to make table name equal to new, table space name equal to new table space. And when I insert into the table, rather than listing out comma delimited column after column after column, values, parentheses, value after value after value, I just go, hey, I know my variable looks exactly like a row in the table. Just slam the darn thing in there. I've saved a staggering amount of coding. I've only done this for a table with 2 columns. I could do this just as easily for a table with 200 columns, and it wouldn't require any more code. So now, let's take a look at using that concept of using a user-defined data type to substitute for column, comma, column, comma, column, comma, column. Let's take a look at how in PL SQL you should do insert statements. And the difference here is pretty dramatic. What I've done here is I have again defined a data type that looks like a row of my table. My type is called myArray, and it's a table of rows that look exactly like my parent table. I open a cursor, and now you'll notice I have a batch size of 1,000 rows. What I'm saying is instead of going through and selecting one row at a time and inserting one row at a time, I'm going to load an array with 1,000 rows. I'm going to grab 1,000 rows. I'm going to process 1,000 rows. When I insert, I'm not going to do 1,000 insert statements. I'm going to do one insert statement. And that one insert statement is going to write 8K blocks. So you have a choice. Let's assume your average 8K block holds 100 rows. You could do 1,000 inserts, or you could write 80K. And not as separate insert statements, but just, I'm going to write 80K, 8K, 10K blocks. Then, I'm going to batch process, check all the primary key constraints, check all the check constraints, check all the foreign key constraints, fire the trigger, update the index as a single batch operation. It is amazingly fast. There are other clauses that go with this, like the save exceptions clause and the partial collections and sparse collections clause, which you want to be aware of. But on an IBM, not an IBM, on a Lenovo T460 laptop, I can run the statement that you're looking at right now, and I can insert 500,000 rows per second every day of the year. And if it wasn't for the fact that we have a little problem with me going live and letting you see my screen, right now, Francisco is showing the slides from his so that you can see them. I could live demo this for you right now, and I could easily break 500,000 inserts per second. It is trivial to do so, and all of the code for doing this is in the morganslibrary.org website if you look up array processing. Now, there are other versions of the syntax. So on slide 46, I have another version that uses a array, which is an index of binary integer type of array. And on slide 47, I use an array that I created by using some DBMS SQL arrays and merging them together to create what I want. But essentially, they all come out with being able to hit roughly that 500,000 rows per second or above with the sample data that I use for this. Let's go to slide 48. I mentioned I would mention the merge statement only one time, so I'm going to do that here. And just to show you that you can, in fact, use this bulk collect and for all statement with merges as well. So this is a for all merge into. So that's all I'm going to spend time on that. I've got some things here on 49 and some others that I'm going to go through pretty rapidly so that we hit roughly our time mark to have this end roughly on time. So I'm just going to briefly mention what's here as I go through, and then we'll slow down again, and I'm going to spend some time on some additional slides. Slide 49, large objects. Slide 50, showing how to do dynamic SQL inserts with the DBMS SQL package. The critical thing I want to point out to you on slide 50 is the returning clause, which allows you, without querying your table, to bring data about that table and about the insert you just did back to your application. Native Dynamic SQL can be used for inserts. Native Dynamic SQL can also be used with the returning clause. And I have to confess, I'm reasonably proud of the statement you're looking at right now, because this wasn't easy to write. It was one of those things where I looked through the entire internet and could not find a single example of anybody ever actually posting how to do this, and I made numerous mistakes until I finally figured out what I had to do to make it work. Slide 53, talking about identity columns, which in Oracle 12 showed up as a way to auto-number surrogate keys. Slide 54 is another version of Native Dynamic SQL. This one using Native Dynamic SQL with the returning clause and showing that you have to say returning into twice in order to make it work. So what I want to do now is let's go to slide 56 and then to 57. I want to talk about performance tuning insert statements, because I keep hearing you can't make insert statements go faster. Well, clearly if I can do 500,000 inserts per second and other people can't, then maybe there is some things that you can do to make inserts go faster. One of the most important things you can do to make insert statements faster and to make subsequent activities, whether it's select or update or delete faster, is to stop using wide tables. Oracle says you can have 1,000 columns in a table. Microsoft says the same thing. I would say, yeah, if you're a magician, maybe you can get an audience to believe that. But the truth of the matter is that realistically, a table may be able to have 1,000 columns, but a segment can only have 255. So as soon as you break 255 columns, you've really bought another segment which now needs to be interjoined in order to pull the table columns. Even if you're only going to be pulling the first one or two columns, you still have to join all the other segments to get out to 1,000. So keeping your columns, your tables narrow makes for much, much faster performance. Let's go to slide 58. This one is one of the more critical ways to performance tune your statements. It won't necessarily help you with the inserts, but it will help you with every operation you do thereafter. And that is to understand that Oracle tables are not paper forms. And it sounds like, well, of course they're not paper forms. But yet, almost every application I've ever seen in my life, and I might be bolder and say, in truth, every application I've ever seen in my life, treats Oracle tables like they are paper forms. We put the first name before the middle name. We put the middle name before the last name. We put address 1 before address 2, then city, then state or county or country or whatever it is. And then we write where clauses that say things like, give me all the people who are in Perth, Australia, which means that Oracle had to read through first name, middle initial, last name, address 1, address 2, to get to the city, to get a few more columns, and to get to the country. So the example I have here is based on the United States. And let's say I wanted to find all the people who were where I am today, Atlanta, Georgia. If I wanted to do that, and I'm assuming here I don't have a B-tree index that just happens to magically correspond to that, I have to parse through person ID, 20 bytes, or 20 ticks of the CPU clock. First name, I'm at 40. Middle initial, 60 ticks of the CPU clock. Last name, 80. Address 1, address 2. By the time I get to state, the state of Georgia, I've used 160 ticks of the CPU clock. That is an inviolable rule. You just ate CPU. If I reorganize the table based on the nature of how my queries are actually written, and I think to myself, nobody is ever going to write a where clause that says, give me all the people whose middle initial is A, or give me all the people whose address 2 column says second floor, number 603. Never, ever going to have that. So why don't I stick those at the other end of the table and never have to spend 20 ticks of the CPU clock to get to those values and parse over them just to figure out what's going on in some later column? And the answer is, I can do the exact same query for half the CPU just by reorganizing my columns to correspond to how the computer works rather than how a human being sitting down with a piece of paper and filling it out with a pencil or pen would fill it out. And why do I care about saving 80 ticks of the CPU clock? Suppose I have 100 million records in my table. Suppose I remember the fact that I pay Larry Ellison and Oracle Corporation for CPU licenses, and that when I waste CPU, I am paying them money both for the original licenses, for the hardware I'm running it on, and for the support agreement. And every single time for the next 20 years, somebody runs that SQL statement and uses twice as much CPU, Larry gets to buy a new part for his next America's Cup boat. That's why you need to be paying attention. It makes sense to be more efficient. So let's go to slide 59. I want to show you how critically important this is. And what I did was I ran a 10046 level 12 trace. And I used a table that's in Oracle 12102 that has 193 columns in it and only one row. So the table is Apex 040200 WWB flow page plugs. It only has one row, so everybody's got the table and everybody can run this query themselves if they want to. Just select the column, the value of the first column, and then select the value of the 193rd column. The first one, 13 bytes. The second one, 2002 bytes. If I can get the answer by parsing 13 bytes versus 2002 bytes, I think it's going to be a lot faster. If I look at the amount of CPU, the first column uses about half the CPU. Now, you think to yourself, well, maybe Oracle got more efficient with 12.2. Maybe Oracle's going to get more efficient later this year when they release Oracle 18. So here's what you're going to find. I can't show you the numbers from 18, but I can show you the numbers from 12.201. On the left, looking at the 100 at the first column, and on the right, looking at the 101st column. And again, all the information as to which table I used and which columns is all contained right here. The CPU scan cost for the first column, $85,000. The CPU scan cost for the 100th column, 101st column, almost $250,000. 3 times as much CPU used by not putting my columns where they are most quickly accessed. Let's go to slide 61. This is just some general information you'll want to be aware of. Just because you do not have to alias schema names doesn't mean that you can't make things faster and more efficient by doing so. When Oracle says you don't have to, what Oracle is essentially saying to you is, no, you don't have to, because, hey, we'll do it for you. Oh, yeah, but when we do it for you, we're going to waste CPU and it's going to be slower. And that's always the rule when Oracle says you don't have to. So if you take a look, for example, at slide 62, both of those insert statements are perfectly valid from the standpoint that they won't generate exceptions. In one case, I spent an extra second of my life and wrote _date and explicitly cast a string as a date. And in the other case, I said to Oracle, hey, when this doesn't work and you fail, go back and fix what I didn't do. Oh, by the way, fix it on every single row for the next 20 years. I'm paying Oracle Corporation in CPU and in licensing for what I wasn't willing to spend 1 second casting myself. So will Oracle fail? No. Will Oracle provide a penalty to you for letting it clean up your mess? Absolutely. Slides 63, 64, and 65 are essentially some good information about hints. Memorize slide 63. There'll be a test on it for the rest of your life. Slide 66 is another new insert-related hint that Oracle introduced in 12.1, as is slide 67. I want to spend a minute on slide 68. Another way of making things faster when you're doing inserts is to not let exceptions slow you down. Oracle has, for a very long time, and I'm talking about going back to probably Oracle 9, had a built-in package called Dbms Errorlog that allows you to insert massive amounts of data. It will never, ever fail and generate an exception because of a constraint violation. What it does is it automatically takes the rows that failed and puts them into an error logging table. It's fully and completely automated, and then you can go back later, find the rows in that error logging table, and you can delete them or you can fix them and insert them. But if you know that you're going to insert 1 million rows of data and 3 of them might fail, why not just get all of those rows in there, let people start working, and go clean up the 3 rows later, as opposed to writing massive amounts of exception handling. So slides 68 and 69 show how to do this. And again, the DDL and an example are on my website at morganslibrary.org. Feel free to just go grab the source code there. It's also here in the slide, and try this out, and I think you'll agree this makes a lot more sense when you're thinking about efficiency and performance. I'm going to skip over some of the slides, 70, 71, 72, that group in there. Again, we're running a bit short on time, and I do want to wrap up now because it's been just about exactly 1 hour, within a minute or two of, and I always like to end on time. And let's go to my slide number 75, which is my conclusions. I normally present this where I'm in the same room with the people who are attending the presentation. And I always ask the question, now that you've seen the full syntax of Oracle and all the considerations in Oracle around insert statements, how comfortable do you feel about your personal knowledge of Oracle updates and Oracle deletes? And I get a staggering amount of people shifting in their chair and a lot of really, really nervous laughter because they experienced the same thing I did when Tom Kite made that comment many years ago of, hey, even I don't know all the syntax for insert statements. I have to go look it up. And it was like, yeah, there's a huge amount. I should know. I feel like I should know, and I don't know. So let me relieve a little bit of that stress. There are some things about update statements that you probably do not know. There is probably almost nothing in delete statements that you do not know. So you can feel pretty comfortable that you really have mastered delete statements. The returning clause works on delete statements, probably something you should be aware of and really valuable. Returning clause and some of the others work on updates, and there is a lot of opportunities within the context of both SQL and PL SQL to vastly improve the performance of both update and delete statements. The most important thing that I want everyone to take away from this seminar is that the difference between programs or applications that perform really, really well and those that are a performance tuning nightmare is often not the hardware. It'd be nice if it was everything was running on an Exadata, but nobody's buying me an Exadata this afternoon just because I want one. It's probably not always related to the fact that I'm on the fastest solid-state drive in the world as opposed to 15K RPM spinning disk, or the fact that I've got a 10 gig Ethernet connection rather than a 40 gig InfiniBand connection. What it often comes down to is that given the resources that we have available, we waste staggering amounts of those resources. We waste them by doing select statements and merges that we really never needed to do. We waste them in doing exception handling that could have been addressed with the Dbms Errorlog table. We waste them by not using the PL SQL syntax with bulk collect and for all but doing the SQL one row at a time. We, in essence, create the bottlenecks that we then spend a lot of our time worrying about, or working on, being frustrated with, listening to people complain about. So when you look at a problem, it's not always just about rewrite the SQL statement. Often it's look at the whole problem. Are the columns in my table properly ordered? Is my storage properly separated in a way where things are not conflicting with each other? Is every index a B-tree index? Well, that's probably not the right answer. I might not need B-tree indexes for every index. Is every table a heap table? Index organized tables provide huge value. And if you haven't got at least one or two index organized tables in an application, chances are there's an opportunity there to optimize as well. So keep all of this in mind. What you want to do is minimize the amount of work. You want to work so that the computer doesn't have to. And the more you can use your efforts, because you're still smarter than the computers we work on by an awful lot, to then turn that equation around, you'll get the kind of performance you're looking for. And with that, let's go to the last slide. Francisco, I want to thank everyone for attending today. I hope you all got a lot out of it. And if there are questions that come out of reviewing these slides, feel free again, email them to Francisco, email them to me. I'm more than happy to answer any questions that I receive. And Francisco, the baton is back to you.
Share our knowledge with the Oracle community around the world.
Thank you very much, Francisco. Good night.
Good night. Bye-bye.